Okay, we're going to look at a few more problems. So one more from page 145, excuse me, 147, and then some from the economics, and then another one involving the cone inside of a sphere. So number 15 here, we're looking at a speed distance problem. So a train leaves the station at 10 a.m., travels due south at a speed of 60 kilometers an hour. Another train has been heading due west at 45 kilometers an hour and reaches the same station at 11 a.m. At what time were the two trains closest together? So you have to draw out the situation here. So here is the situation. Basically, you've got train 1 leaving this station and train 2 heading towards the station. Okay, so 45 kilometers away. So its position relative to there is going to be 45 minus 45t, because it is traveling at 45 kilometers an hour, and distance equals speed times time, right? So d equals s times t. So it's going to be 45 minus 45t. So the distance was 45, and it starts going closer by that amount. This one is starting there, so it's starting at 0 plus 60t, because it's traveling at 60 kilometers per hour. So it's heading away from there. This is the distance between the two. So at any time t, this is the distance. Okay, so basically we have the distance between 2 points formula for this one, or Pythagorean theorem. Okay, so Pythagorean theorem, because those are at right angles. So 60t squared is that distance, plus 45 minus 45t all squared is that position. Okay, this is the hypotenuse, so we're going to square root that. So that is our formula after expanding it, simplifying it. Taking the derivative, it's a chain rule, so bring the 1/2 down in front, reduce it by 1, and then times the derivative of the inside. We've got this function now, this rational function with a square root on the bottom. We want to set the derivative to 0, so we set the derivative to 0 and solve for time. And we get time equal to 21.6 minutes. So they are closest at 10:22, because you want to add 22 minutes, basically, or 21.6 minutes to 10 a.m. So that's that one. Now we're going to go to questions on page 152, and I'm just setting them up because at this point you should be able to take the derivative and solve. Okay, so page 152, number 6, well, it is right here. So number 6. Okay, so real estate office manages 50 apartments, downtown building. When the rent is $900 per month, all the units are occupied. For every $25 increase in rent, 1 unit becomes vacant. On average, all units require $75 in maintenance and repairs each month. How much rent should the real estate office charge to maximize profits? Okay, so we need to set up this formula here. Okay, so we've got let x be the number of $25 increases. Then the rent is 900 plus 25x. The profit is 900 plus 25x minus 75, minus the cost. Okay, so it's $825 plus 25x per apartment. The number of apartments rented is 50 minus x. So when it's 900, it's full. For every $25 increase, it goes down by 1 apartment. So the total profit would then be n times p, the number times the p. Okay, so t equals n times p, which is the product of these two. Now you're going to expand, take the derivative, and solve. Similar for question 7. So this is about a question that has 50-cent increases for tickets. Okay, so for every 50-cent increase, they lose 200 tickets. And the cost per ticket is going to be $20 plus 0.5x, so 50 cents for every increase. So the revenue is going to be that times the number of tickets. Okay, and that's the function that you'd need to maximize. Now, for this question here, this is a sphere with a right circular cone inside. The sphere has a radius 10. Okay, so the constraint for this one is from that center of the sphere to this point is 10 centimeters. This is the radius of the cone, not 10 centimeters. The height is going to be 10 plus this L here. We know that L squared plus R squared equals 10 squared from Pythagorean theorem. Okay, we simplify that and we sub in that H equals 10 plus L. Well, we get now a formula for H in terms of R. And the volume of that cone, so we want the cone with maximum volume. The volume of that cone is pi r squared H. Now we've got a relationship between H and R. We're going to plug in the formula for H here. We take the derivative. It's ugly. Okay, take the derivative, simplify it. Okay, and then at this point you set it to 0 and solve. Because this is going to be pretty hard to solve, I might back up and see what it might be in terms of finding R squared in terms of H instead. So I'm going to try and do that. Not that this is impossible to solve, but it doesn't look like fun. So what I'm going to do now is rewrite that constraint. Instead of using what I've got here, L squared equals R squared plus 10 squared, I'm going to solve for R squared. So R squared is going to be 100 minus L squared, which is what I've got here. When I simplify that, it's a whole lot nicer. It's just a polynomial in H. Okay, because L is H minus 10. When you look at the diagram here, L is H minus 10, because that's 10 along there. Okay, and now we can sub that into the formula for pi r squared H for the volume, and we get this nice formula here. Take the derivative, set it to 0, and we've got H equals 0 or 40. So 0 obviously is a minimum. 40 would give you the maximum. And then we sub that in and we can find R, and we've got the dimensions of the cone with the maximum volume inside that sphere.